Hi, this video is to show you how to work on problem 3 from page 27 of our class notes on statistical process control, also called quality control, and that's the problem we have in our PDF files. So here's the problem. We're going to work on this problem in Excel. So I'm going to start typing these numbers here. I'm going to copy like these numbers from the problem. So we have different samples, 1, 2, 3, 4, 5, 6, 7, 8, 9, and we have the time it took to process the loans, 15, 11, 13, 9, 14, 11, and 13. So I start copying these numbers, and now I know from the problem, because the problem here says a quality analyst wants to control the time in minutes that takes for customers to be served by a bank's loan officer. From previous research showed that the standard deviation of individual customers' times is 4 minutes. So we know that the standard deviation is 4 minutes. After taking 9 samples of 4 customers each, so we know that the size of the samples is 4. We have these numbers, so we have to compute the mean. So the mean is going to be equal average, the time it took in all those samples of 4 customers. Okay, and it says calculate trial upper and lower 3 sigma control limits of the X bar control chart. Okay, so what this is saying is the upper and lower control limit and lower control limit. So I'm gonna use the formula I have here. Okay, so the control limits are the average plus and minus 3 multiplied by the standard deviation of the information we have divided by square root of n. Okay, so let me implement that. So is going to be equal to my mean plus 3 times, because it's 3 sigma, multiplied by the standard deviation divided by the square root divided by SKRT, open parentheses, the sample size of each sample. Okay, so I close 1 parenthesis, 2 parentheses, because I open 2 series of parentheses within each other. So the upper control limit is 18, and the lower control limit is going to be equal to my mean minus, because now is the lower control limit, minus 3 times, because it's 3 standard deviation, open parentheses, my standard deviation divided by SKRT, open parentheses, because that's the square root of 4, close parentheses, close again, and that's the upper limits 3 and 6. So solution 18 and 6. So this is how you solve this problem. Okay, now plot the control chart. To plot the control chart, what I suggest you to do is you can copy this, or you can do it there, it doesn't matter, and then you type here UCL and LCL, and then you type 18 and 6, because those are the upper and lower control limit. You select the cells and hold with the mouse and copy all the numbers, and then what you have to do is select these cells here and go to insert, and then select this line, and then you have here the control limit. Then you can edit the chart. I'm not going to spend time editing the chart, but you can edit the chart X bar control chart. Okay, all right, let's go to the third question. The third question is this process under control? What should she do in this situation? So it's in control because all the samples 1, 2, 3 up to 9, they are within the control limits. So what she can do is keep working like this, maybe training people to keep working as they are, and so forth. Okay, so let's move on to the next question. Every how many samples will she get a false alarm? Okay, so in this one, what we are going to do is kind of work with the type 1 and type 2 error. So this is type 1 error. Oops, type 1 error. If you take a look from our slides, type 1 error, false alarm. Okay, let's go back. Type 1 error, I have the sigma or the z, the sigma that I want. Right, let's go back to the problem. The sigma is 3, control lower 3 sigma. So let's put standard deviation, standard deviation, standard deviation. 3 and minus 3 around the mean, okay? And then we have to compute as the probability. This is like probability. The probability is going to be equal to norm dot s dist. Then I select this standard deviation type 1 close parenthesis, and I get this is upper tail. So that's not the final probability. I want to know what is like. I want to know if I go back to the normal probability. That's the upper tail. So what we computed in Excel is the cumulative probability, all the shaded area up to this point. So I want to know the complement. So to get the complement, what I have to do is final upper tail. Let's call that final upper tail. Okay. So this final upper tail is going to be equal 1 minus this number. And for this one, the probability is norm.s dist, this number, and then 1 close parenthesis. So the final upper tail is going to be this number anyway. So what I computed is the probability up to the lower tail, and then I computed the probability on the upper tail. So I'm going to sum these two numbers to get the whole probability. So the sum, let's put here, sum is equal to this plus this. Sum, let's call sum of the tails, all of the tails. And let's call this standard deviation, or z. Let's call z. Upper and lower. Okay. Let's do this just to make it clear to you. Upper, lower. This 3 comes from the problem. So the problem says upper and lower 3 sigma control limits. Okay, so this is where it's coming from. And then we have the sum of the tails here. Now we're going to compute the probability. Oh, I'm sorry. This is the probability. Now we're going to compute and answer the question of every how many samples will get a false alarm. So every how many samples. Okay, this is going to be equal to 1 divided by this probability. So if we divide 1 by the sum of the probability on the tails that are not included in our control limits, we get 370. Every 370 samples we get a type 1 error. Okay, now let's move on. This is the answer we have. It's here, every 370 samples. Now let's work on this one. The analyst only wants to get a false alarm every 500 samples or more. What sigma level, what standard deviation should she use? Okay, and let's compute the, so let's do this. Let's get a false alarm only every 500 samples. So N and P, let's call N is 500. So my P is going to be, what's the probability of having 1 false alarm every 500? So the probability is 1 false alarm divided by 500 samples. So this is 0.002. And if we go back to the normal distribution, is the probability that we can have in maybe the lower tail, the upper tail, they will be we are going to have a sample that has a very low or very high mean, and we might think that it's a problem, but in fact it's not. It's just because of variability in the sample. And then that's the probability of getting that 0.002. But we have to divide that for each tail because it can be higher or it can be a little lower, okay? So what we do is equal this number divided by 2, okay? And now we get the standard deviation, which is our sigma. So let's copy this. What is the standard deviation, or z, associated with this probability in each tail? So going back to the normal distribution, remember, if we have a standard normal distribution, here is 0, here are negative numbers, here are positive numbers. So what are the z associated with such low probability, and what is the z associated with the high probability? So how we do to find that is equal norm dot s dot inverse open parenthesis, and then we get this number here and close parenthesis. So the probability is almost negative 3.1 or 3.1 standard deviations. If we reduce the number of decimal points, then we get 3.1 standard deviations below, and this is below, but also we can say that we have above because we have for both sides. So this negative 3.1 is going to be negative and positive because it's both tails, okay? Now let's compute the new upper control limit and then new low control limit. How we compute the new control limit is going to be equal to the mean plus, because it's the upper control limit, so I have to add 3.1 because this is the standard deviation, and if it is upper, it's going to be right positive multiplied by open parenthesis my standard deviation divided by the SQRT open parenthesis the sample size, close parenthesis, close again. That's 18.2. The new low control limit is going to be the mean minus 3.1 standard deviations multiplied by the standard deviation divided by the square root of the size of each sample. Then I close parenthesis once, I close parenthesis twice, and I have the new upper control limit if I want to have a false alarm only every 500 samples. And that's what we have here. So this is the solution, 18.2, 5.8. So this is how you found it, and that's it.